The question reads, a locomotive is pulling a train with a mass of 150 ton up a hill with an incline of 10 degrees. At a constant velocity, if you see the constant velocity, we know that the acceleration is equal to 0. 72 kilometers per hour. Okay, 72 kilometers per hour is not in our MKS format. We need to convert that to meters per second. The train experiences a frictional force of 8,000 newtons. Calculate the power required by the locomotive to pull the train. So first things first, let's convert all units. Then we will do a drawing, and then we will do the calculation. So let's convert 72 kilometers per hour is equal to 72 times 1,000, because kilo means 1,000, divided by per hour, and I want it in seconds, so it's 60 seconds in a minute, 60 minutes in an hour. 60 times 60 is 3,600. So let me get a calculator, and we can just see what we get now. Calling up the calculator here. We have 72 times 1,000 times divided by 3,600. Divide gives us a nice round answer of 20 meters per second. Okay, so now we've converted. All values are converted. Let's draw a diagram. So this locomotive is pulling something 10 degrees to the horizontal. Let's draw it here. There's my mass. It's going up the hill. What do we know about the mass? The mass, they told us, was 150 ton. So that's coming straight down. 150 ton. That's the force due to gravity. Also, the train is pulling a force going up. It's called that F pull, because it's doing work to go uphill. But there are two forces working against it. Friction, the force due to friction, and that has a value of 8,000 Newton. But we also have another force, which is the parallel component, F parallel. Remember, that is the component of gravity working on the plane of action. So we also have the perpendicular component, F perpendicular. So the question says we're asked to calculate the power required by the locomotive to pull the train. So the only forces that we're interested in are the forces acting in the plane of action, and that's at the 10-degree plane. So what do we have to do? First of all, we have to calculate F parallel, because I need to know the value. So F parallel is equal to, and if you remember, it's mg sine theta. We know the mass of the train was 150 ton. Again, that must be in kilogram, so it must be 150,000 kilogram. Why? Because there's 1,000 kilogram in a ton. Times gravity, 9,81, times the sine of the incline, which is 10 degrees. Let's call up the calculator. Let's punch in those numbers. Make sure your calculator is in degrees. We're not working in radians anymore. So we have 150,000, 9.81 for gravity, multiply, and we have the 10 of sine. Multiplied. Let's get a number. That gives us, whoa, what a big number. I'm going to do shorthand, 255,2 kilonewton. Obviously what I'm going to do on the calculator, I'm going to keep all of those decimals. I'm not going to remove any of the decimals. Keep them in there. You have memories on your calculators, so use the memory. But just to show what I've written down, it's in kilonewton. So we want the power of the locomotive. There's a force which is pulling the locomotive up. So what do we know about power? We know that power is equal to force times velocity. Did they give us the velocity? Yes, we have it. It's 20 meters per second. Do I know the force that is being used? Well, yeah, we do. The force, because there's no acceleration, so the pulling force must be equal to all the forces working against it, because the net force is 0, because there's no acceleration. So if I have F pull here, and I have two forces here, one is 8,000, and we've just worked out the other one, 255,2 kilonewton working against us, what will the pulling force be? So we can now write a very nice equation. The power required must be equal to the pulling force multiplied by the velocity. And the pulling force will be the 255,2 kilonewton plus the 8 kilonewton, which is the friction, all multiplied with the velocity, which we've worked out in meters per second. Remember, everything is always MKS, meter, kilogram, second. Don't forget it. Now we need our calculator again. Let's move it out the way and we can see what we're doing. So I've kept all the decimals, they're still there, plus 8,000. And I need to multiply that with 20. Wow, what a big number. 5270465. Oh, okay, I'm not going to write all of those. Let's write it in scientific notation, or engineering notation, I think would be a better one. 3 decimals. So this answer is 5,2 mega, because it was a 6, watt. There we go. So the power required by the locomotive is 5 point, well, we can write the 7 in, 5,27 megawatt. Okay, I think that's it. Go through the questions, please, work through it. This is an interesting question. Remember, always convert all your units to MKS, meter, kilogram, second.